In this video we have a look at how to solve for angles and sides in non-right angled triangles. Before we have a look at the formula that we use, let's have a look at the notation we use to represent the sides and the angles. Now we use lowercase letters to represent each side and a capital letter to represent a vertex where the angle is located. So we can see in this diagram that lowercase a, representing the side on the upper left, is opposite the angle in the bottom right hand corner, which is shown with capital A. And if we extend that further for A, B and C, we can see that the capital letters are in the vertices of the triangle belonging to the angles, and the sides opposite them are the same letter but they're in a lowercase version. So the first rule that we're going to have a look at, it's one of two rules, is the sine rule. In this video we won't have a look at the development of the formulae, but what we'll do is we'll go through and apply them to some examples. So the sine rule that we have in front of us here we can see is expressed as fractions. So we have the side over the sine of the opposing angle. And it's also true that that same formula works when we have the sine of the angle over the opposing side. So both of those formulae work for the sine rule. The cosine rule uses sides A, B and C as well, but incorporates them with the cosine of the angle opposite the side A. So the critical thing to note in this formula is that the side A, which is on the left-hand side of the formula, is equal to the expression on the right-hand side where the angle matches the initial side, in this case A. We can also express the cosine rule such that we can find the angle quickly. So we can express it as cosine equal to an expression with the sides A, B and C. So let's have a look at an example and see how we determine whether to use the sine or cosine rule and how we apply that particular rule in each case. In this diagram we know two of the angles and we know one side, and we need to find the other side labelled with an X. Now in any situation where we have a triangle where we have two sides, admittedly one of them may be unknown, we need to find it, and we've got two angles, or at least we have two sides and two angles, we can use the sine rule. Now there are two versions of the sine rule to use. We saw that previously where the lowercase letter, in other words the length of a side, is the numerator of the fractions, or where it's the denominator of the fractions. So we'll use the one where it's the numerator in this case. It's just easier when we need to find a side and the unknown is a numerator. If you're using a programmable calculator with preset formulae, it really doesn't matter as long as you substitute the correct values in. Now when we use the sine rule, the formulae contains all three sides and all three angles. But it is sufficient just to go with two sides and two angles. Once we substitute the values that we know in, we should be able to solve the equation for the unknown. So we'll cross off the last part of the sine formula, and we can do that as an ongoing process. Just use two sides and two angles in our formula. Now substitution does need to be careful because we need to make sure that the angle and the sides which are opposite each other are what goes in each part of the formula. So we can see here that we've got the side X, which is opposite the angle of 120 degrees, so that goes into the left hand side of our formula, and the side 10 is opposite the angle of 25 degrees, so that goes into our right side of the formula. Now if we're using a programmable calculator, this is a very simple process. Now you should just be able to press solve and the answer will come out. But if we're solving this algebraically, what we'll do is we'll multiply the sine 120 degrees across to the right hand side, and then we'll solve that on our calculator, and we should get an answer of 20.49 meters. This is of course an approximate answer, and you should always check to see what the desired rounding is for each particular question. So in our next example, we'll have a look and see that we've got two sides, 5 and 11 millimeters, a 52 degree angle, and we're trying to find the angle at vertex A. So in terms of our information, we have two sides, two angles, admittedly one angle we don't know, so that tells us we can use the sine rule. Now given in this case we're trying to find an angle, what we'll do is we'll use the sine rule such that the fractions are inverted compared to what we used in the previous example. So we've got sine of the angle A over 5, because 5 is the side opposite the angle A, and we've got sine of 52 degrees on the right hand side, and that's over 11 because that's the opposite side. Now, solving this problem using a calculator, we can go through and just do a simple push the button if it's a programmable one. But if we're solving this algebraically, we'll take the 5 across to the right hand side by multiplication. And when we do that, we get an angle of 20.99 degrees. Of course, that involves using inverse sine as well, which we won't go through in this particular video. Now, what we need to be careful of is that when we're solving for angles in a triangle, knowing how the unit circle works for sine, we know that 20.99 degrees is in the first quadrant. But sine can also have a positive value in the second quadrant, in other words, an angle between 90 and 180 degrees. And given that angles in the triangle can be up to 180 degrees, we need to check for that second angle. So doing that, and using the unit circle, we find that the second angle could be 159.01 degrees. And the key here is to note that whenever we're using the sine rule to find angles, we do need to check for two angles. The question is, though, are both answers appropriate? Now, if we look at the angle of 159.01 degrees and put that into the triangle, we'll notice that the sum of the two angles that we now have exceeds 180. In fact, we get an answer of approximately 211 degrees. Now that's a contradiction. We can't have a triangle with angle sums exceeding 180 degrees. So that means in this case, that second answer can be ignored. But the key thing to note is we must always look for two possible solutions when we're finding angles using the sine rule. Now let's have a look at another example. Now in this case, what we have is two known sides, 6 and 8 meters, a known angle of 80 degrees and an unknown side. So in terms of the information that we know and also what we're trying to find, we have three sides and one angle. Now when we get this type of information, in other words 3 sides, 1 angle, it means that we can use the cosine rule. So we'll write the cosine rule formula down and then we'll perform our substitution. Again, we need to take care to make sure that we have the angles in the appropriate spot in the formula such that the unknown side is opposite the given angle. So when we do our substitution, it doesn't matter which sides we call B and C. So in this formula we've substituted 6 for B and 8 for C. That doesn't really matter. We could have had 8 for B and 6 for C. The key thing is that the B and C in this formula are the sides that are adjacent to the given angle. It might be wise to pause here and actually go through and check to see that you understand the matchups in terms of lowercase a, b, c and capital A. And when we solve the answer, a good idea would be to solve using 6 and 8 switched. In other words, let b equal 8 and c equals 6, just to convince yourself that it doesn't really matter which values b and c are as long as they're the ones adjacent to the given angle. So if we go through and solve that on our calculator, we get an answer of 9.13 meters for the unknown side. Let's have a look at another example now. We can see that we've got 3 sides and one unknown angle at vertex A. So again, because we have 3 sides and one angle, admittedly one we're trying to find, we can use the cosine rule. Now if we're using a programmable calculator, the previous form of the cosine formula will be sufficient and we can do the substitution, and through a simple press of the button we should be able to solve it. But if we're trying to rearrange the formula so it's easier to find the angle, we can rewrite it such that we have cosine A in terms of the unknown sides. Let's stick with the original formula. So we'll go through and substitute into that. And the thing we need to be careful of is that the value A for the angle is opposite 14. So lowercase a is 14 meters. And again, it doesn't matter which values B and C are, they're the sides adjacent to the angle. Now for solving the unknown angle A, we have actually missed a couple of steps here because this does involve some algebraic rearrangement or using a programmable calculator solving for the angle A. So you may wish to pause at this point and check to see that you agree that the answer is 103.00 degrees. Now we saw previously in the example with the sine rule that if we had an angle answer, we needed to check for 2 values. Now in the unit circle, cosine is positive in the first quadrant, in other words angles up to 90 degrees, and negative in the second quadrant, angles up to 180 degrees. So because we get different signs for cosine in the first and second quadrant, in other words positive and negative, what we know is that the angle answer we get is unique. so there's no need to check for a second angle. So in this case, the unknown angle at vertex A to 2 decimal places is 103.00 degrees.